up with your microphone now? A sign? Yeah. I don't have it. I can get you an iPad if you want. Okay. I can slide papers and stuff. You can just raise your hand. Yes. Yeah, okay, our stream is fine. It's hard to find something.
Yeah, kind of. Or it goes like around corners.
Let's make sure no questions go into the microphone.
Okay, should we start? Okay, so welcome everyone to research session 9 for database for new hardware session. Since you have made it here, congratulations, you have solved the maze. It was not easy to come, and you should be proud finding the room here. Took some time to get it. Okay, so we have 4 talks, 4 European talks, so that's kind of a European session. Welcome to Chicago. And the 4 talks are about new hardware. We start the first talk titled Accelerating Pattern Matching Queries in Hybrid CPU FPGA Architecture. That looks so interesting. It's from ETH Zurich, and the presenter is David Sedler.
Yes.
25. We have 20 minutes and 5 minutes for questions.
Okay. So thank you. Welcome to my talk about accelerating pattern matching queries in hybrid CPU FPGA architectures. This work was done together with Scholt, who sits over there, Mushen, which is a postdoc in our group, and our advisor, Gustavo Alonso. So there is an increasing amount of user-generated data. For instance, user tweet, they comment on different type of things, and they write product reviews. And most of this data is text data, and it's also partially stored in relational databases. However, relational databases are not performing very well when it comes to complex string operations or text analytics, and we can illustrate this on a simple example. So here we look at MonetDB and a commercial row store, which we call DBX, and we have 2 queries. The first query is a like query, where we do substring matching on 3 substrings, and in the first query we use a regular expression operator, and we actually do the same substring matching on the same 3 substrings. So the result of this query is going to be the same. However, by just going from the simple operator to the regular expression operator, we see that the response time increases by a factor of 20x. So relational databases are really not suitable for complex text queries, and one way to address this is by the use of accelerators. And there's actually existing work using GPUs or Xeon Phis to accelerate string matching, and in fact they report the high speed up over CPU-based implementations. However, they have to make some assumptions, and one of them, for instance, is that the data is already local to the accelerator, so it's stored on the accelerator. Or once they actually would consider the data movement between CPU and the accelerator, the benefit of the acceleration is heavily reduced. Some approaches also requires that the data layout is adapted to the execution model of the accelerator, or with increased complexity of the patterns, we see like generally reduction in performance. But more importantly, generally it's often not clear how would we actually integrate such an accelerator into an existing database engine. And the reason for this is that when you introduce the accelerator to the database, you either have to partition your data between the CPU and the accelerator, or you have to move it back and forward. And this really introduces an overhead which hinders like the widespread adoption of database accelerators. However, there is now new hybrid architectures emerging. For instance, we have from IBM the Power 8 system, which comes with copy, where the accelerator gets cache coherent access over PCI Express. Or on the other side, we have from Intel the Xeon Plus FPGA platform, where the FPGA is connected over QPI and can access direct memory. In both these architectures, now the accelerator has cache coherent access to the main memory, and thereby we remove the need to move data back and forth or partition it, since we have this direct access. And in this work, we're going to use the Intel Xeon Plus FPGA prototype platform, in particular version 1. And this is a machine which has 2 sockets, and in one socket we have a Xeon, Intel Xeon with 10 cores, and in the other socket there is an Altera Stratix 5 FPGA. And these 2 sockets are connected over QPI, and main memory is we can only install main memory on the socket of the CPU. And that means that the FPGA has to always go through QPI if it wants to access the memory. And for read-heavy workload, we measured around 6.5 gigabytes read bandwidth. And if we have a mixed workload, 50% reads, 50% writes, we get around 3 gigabytes in each direction. But here I also want to mention that there's actually already a new version out, the HARP version 2. And there, some of these limitations are already addressed. So you will get higher bandwidth from the FPGA. There are 2 more PCI lanes between the Xeon and the FPGA. The FPGA is newer and correspondingly larger. And very importantly now, this is all in one socket, so there's not one socket occupied by the FPGA. So although FPGAs are becoming more popular, I still want to give you a high-level overview of how they actually work. So as the name says, there are field programmable gate arrays, which means we can program them with an arbitrary circuit. And once they're programmed, they act similar to an integrated circuit. However, they run usually at a much lower frequency, somewhere in the range to 100 to 400 megahertz. And internally, they consist of an array of configurable logic blocks, the orange blocks here. And this array is also interleaved with on-chip memory, which is called block RAM. And these are the green blocks here. And to connect either the logic blocks with each other or the logic blocks to the on-chip memory, there is a configurable routing network. And when the FPGA is programmed, this routing network together with the logic blocks are all configured. So let's go to our regular expression engine, or more importantly, how we actually make it parameterizable in hardware. So there's already a lot of existing work using FPGAs for pattern matching in the domain of network intrusion detection or also complex event detection. And FPGAs can do this very efficiently, and the reason is because you can map these patterns to a non-deterministic finite automata, and this NFA you can directly implement in hardware, like you lay it out as a circuit. And in an NFA, since it's non-deterministic, we can have multiple states concurrently active, and if it's done in hardware, this is really truly concurrently, so multiple states can be active. However, in software, generally regular expressions are implemented as DFAs, and there only one state is active at a time. And to illustrate this, we have an example expression here, AB plus or BA plus followed by C, and the corresponding automata. So on the left side, we have the NFA, which is very compact, and on the right side we have the DFA. In this case, the DFA is one state more, but it has also many more transitions. Since only one state can be active, this is necessary. And if we get more complex expressions or large expressions, the DFA will actually grow much quicker in comparison to the NFA. And the larger the DFA is, the more resources it requires. So to illustrate how they actually operate, we have some example input here. So first we consume a character A, and this will activate state S1 in both of them. And then we consume a character D, and that is actually not part of our expression. So again, only S1 is active. And then the third character is again A, so we see S1 is active again. And now the fourth character is a B, which in the DFA, we will just activate state S3, while in the NFA now we actually have two states active at the same time. So S1 activated itself and also activated S3. And then there's more character Bs in the stream. And then finally we have a character C, which in both automatas will trigger the final state. And once we reach the final state, we know that we had a match in our regular for this expression in the input. So this was a very short expression, and therefore the NFA was quite compact. However, we said in the beginning we want to look at user-generated data, and there we look at larger expressions and more text. So let's look at an expression which is more natural language. So we have SIGMOD, wildcard Chicago, or relay, and if we map this to the NFA looks like this. And now we have many more states. And if we map this to the FPGA, each state requires actual hardware resources. And the larger the NFA, which means the more complex expression or the longer the expression, the more of these hardware resources we require. And as you have seen, we actually have to connect them through this routing network. And it might be possible that at some point, the NFA becomes so large that we're not able to connect it and still meeting some frequency. So if you want to run it as 200 megahertz, there's some limit at which, at that point, we are not able to run it at 200 megahertz. And we address this by compressing the NFA. And since we have kind of many states with only one transition and only one state it can reach, we can actually extract these sequences which we have from the natural language. So we extract SIGMOD, Chicago, and relay, and now we can compress our NFA to only 3 states. However, now in this NFA, the transitions are not triggered by a single character, but by the sequence of characters. And to address this, we use something called a character encoder, and thereby we can decouple the state transition from the character matching. And this is something that was used before, but in a different purpose. Essentially, before it was used to save the number of matchers. For instance, if you have multiple times the character A, we would only have one matcher, which would then trigger multiple states which want to observe this character. However, we use it to build sequences of characters. So if we look at our character encoder internally, we have these different characters loaded in, and now we can actually chain them together into a sequence, and only the last character in the sequence, here that's D, will then trigger a state as 0. We are also able to configure them differently such that 2 of these matchers actually build a range together where one of them is checking for the lower value and the other one for the upper value. And then if the incoming character is between these 2 values, they will trigger a state. We also have a flag to support case insensitivity, so we can check at the same time the lower and the uppercase character, and if one of them matches, it will trigger a state. And this can be extended for collations where we would match the same alternations of a character in concurrent, and then if one of them triggers, it will correspondingly trigger the state. And if you look at this architecture, we actually see it would be very easily to switch out these characters and just match a different string instead of SIGMOD. And thereby we are actually able to parameterize this hardware at runtime by just swapping out the characters with different characters. And also these flags are just individual bits. And that's exactly what we are doing. But this is only for the character encoder. So if we look at the whole, how we're going to parameterize the whole NFA. So essentially we build like a generic NFA here in the middle. And this example is only 4 states. And these states are fully connected. And the connections can be enabled and disabled at runtime. And to illustrate how we parameterize this generic NFA with these 4 states and the character encoder on top, we look at the regular expression here, A or B, wildcard C. In general, this would lead to this NFA, but now we have our generic NFA, which we want to parameterize. So first, we extract the characters A, B, and C, and we can load them into this character encoder. And second, we need to know which character triggers which state. So for instance, A and B both will trigger state S1. So in this trigger matrix here, we enable these edges or these trigger edges in the NFA. And then thirdly, we have the state transitions, which are encoded in the state transition matrix, and we can enable these 2 state transitions. So once we have these two matrices, the trigger and the state transition, and also the characters, we can actually just take these parameters and store them in a configuration vector. And this can be done in a very compact format. So for us, this only requires 2 cache lines, so 2 times 512 bits. And then these 2 cache lines we can send to the FPGA such that the regular expressions engine in hardware can parameterize it themselves. And since it's only 2 cache lines, this will only take 2 cycles on the FPGA. So as you might know, the NFAs are only consuming 1 character at a time, or 1 character per cycle. And to get high bandwidth, we actually deploy multiple of them in the regular expression engine, so up to 16s. And we introduced a string router module in the front, which takes the strings coming from main memory and distributes them in round robin to the different NFAs. And then on the other side, we have a module that merges these results in the same order. So the result is either match or non-match, and if you have a match, we also have the position of the match. And then these results get written back to main memory. So with that, I would like to go to the integration into the database. So we integrated this into MongoDB, a column store. And one advantage of the column store is that since we parse the data actually on the FPGA, it's easier to parse the column store, and therefore we need less logic on the FPGA, and we can save some hardware resources. And the layout for strings is we have a string heap with all the strings and some metadata, and we have a column with offsets pointing into that string heap, and this structure is then parsed by the FPGA. Another advantage of using MongoDB is that in MongoDB, an UDF can operate on a complete column, and thereby we can offload the complete column to the FPGA, and we don't have this overhead of calling the FPGA for each tuple. And this reduces the overhead significantly. So let's zoom a little bit out and go back to the whole system. So again, we have the CPU and the FPGA, and they can communicate with each other through shared memory, which is the green box on top. And we have 3 main components in our system. First, we have MongoDB, which we extended with this hardware user-defined function. Then we use Centaur, which is a framework that bridges the gap between software and hardware and essentially provides us a nice interface to create and monitor the jobs on the FPGA. And then on the FPGAs, we are able to deploy up to 4 of these regular expression engines. And each of them can actually process data at 6.4 gigabytes per second, which will already be enough to saturate the QPI bandwidth. So to tell you how these actually interact, these components, we go through a quick walkthrough. So first, let's say a query enters the system, and this query contains a regular expression. So we will call into the UDF, and then the UDF does this configuration vector for the regular expressions and stores this vector actually in shared memory as parameters. Then it will enqueue a job into a job queue also in shared memory, and this job queue is observed by a module on the FPGA, which is called job distributor. So it dequeues that job and assigns it to one of the engines. The engine will then go and fetch its parameters from memory and configure itself with that regular expression and then start the execution. Once the execution terminated, it will update its status also in shared memory, and this can then on the other hand be observed by the user-defined function, which will return the result column back to MongoDB. So with that, I would like to go to the evaluation. So in the evaluation, we looked at 4 queries. And query 1 just does a simple substituting using the like operator, while query 2 to 4 actually do regular expressions, and which are more compute intense. All of these queries cannot benefit from an index and require that we scan over the whole data. So first we wanted to look into the overhead of offloading this or going to the FPGA. And for this, we on purpose took a very small data sets of only 10,000 tuples. So you can actually see the overhead more clearly. You see the orange bar and the gray bar at the bottom. These are actually actual processing of the data. And then in the middle, we have the overhead. So red is for creating the FPGA job. Blue, which is not visible because it's only a few microseconds, is generating this configuration vector, which I explained before. And then for brown is the time we spend in the user-defined function on the software side. And this overhead is actually fixed. So when we increase the data set size, this will stay fixed, and only the processing will proportionally increase with larger data. So while it looks large here, this will get very small if we have larger and larger data sets.
Is this with the same regular expression that you tried with MongoDB and like vanilla without your FPGA? Initially, you had like a slide with the results of MongoDB doing your.
No, these are these four. Okay. So, and as you can see here, actually all four queries have the same response time, and this is because the NFA implementation actually can perform the same independent of complexity, because we just consume the data and the NFA evaluates it. So let's go next to evaluation of the throughput. So first we see on the left we have MongoDB against MongoDB extended with our FPGA-based operators, and we can see that for the simple substring query, actually MongoDB performs better, and this is because the FPGA is actually memory bound, while MongoDB or the CPU has a higher memory bandwidth, and here it can benefit for query 1, which is not compute intense. But as soon as we increase the complexity, the problem is no longer memory bound, and the performance on MongoDB actually starts to drop, and it's around 1 order of magnitude lower than what we have for the FPGA. On the other side, we again have this commercial row store, and in that row store, one client only one thread is used per client, and therefore the performance increases with the number of clients. And we see that only for this simplest query, actually, this database is able to match the performance of the FPGA. And maybe you wonder why we actually compare against 10 clients here. So as you have seen in version 1 of this platform, the FPGA uses a complete socket. So we really wanted to make the socket versus socket comparison. So we have the FPGA in one socket, and in the other socket we have this Xeon CPU with 10 cores, and that's why we have this comparison. And you already see that we are like in the same ball. I mean, for simple queries we are slightly slower, but for complex queries we can easily beat the CPUs. And then in the next generation we actually will have this all in one socket, and you don't have to use one socket just for the FPGA. As we integrated this FPGA-based operator as a hardware user-defined function into MongoDB, you can actually use it in any type of queries. And there's only a few queries in TPCH which use the like operator. One is query 13. And here we just switched out the like operator with our hardware operator, and you see the comparison between MongoDB and MongoDB team with the FPGA, and we measured like the response time of a single query. And you see that we get about half the response time using the FPGA-based operator. But now let's say we want to actually increase the complexity by, for instance, instead of using the like operator, we use the I-like operator, which is case insensitive. Then on the software side, we see how the response time roughly doubles, while for the hardware we get like exactly the same response time. So finally, I want to go back to the accelerators we had in the beginning. So we saw that you can actually do regular expression evaluation on GPUs, but also on Xeon Phis, and we presented how we do it on FPGAs. And on FPGAs, this is actually, the performance is independent of the complexity, while for GPUs and Xeon Phis, usually the DFA is used, and the larger the DFA grows, this will have an impact on the performance. However, if we look at the throughput, so first we look at the throughput if the data is local, we see that if you use a GPU, you might get around 60 to 70 gigabytes in the first approach, which only does string matching, or 10 to 15 in the second approach. And if in the Xeon Phi, you get even more, you get 30 to 40 gigabytes for doing regular expression. And our approach can do 25.6 gigabytes if we neglect the memory bandwidth limitation. And there's no numbers, only for the second GPU work, we get the numbers including the PCI transfer, so there we see that it goes down by an order of magnitude. And in our case, we're not really on the PCI, so we have this 6.4 in this work. But this is not really a comparison among accelerators. So GPUs clearly benefit from their fast GDDR memory, but what we want to show in this work, this is actually the FPGA is no longer an accelerator and becomes a specialized core. It is very close to the CPU, and therefore we have this direct memory access, and we don't need to move data back and forth. And actually looking at the next iteration of Xeon plus FPGA, we see that this bandwidth will increase, so we should get like 20 gigabytes per second, and the FPGAs also become larger and we have much more tighter integration. And we actually believe that in 2 years or so, you might be able to buy this Xeon CPU and you will have an FPGA in there. And one way to use it is doing this regular expression evaluation, and you don't need an external device like a GPU. Of course, you can still do that, but the FPGA will be there anyway, so you might just use it for this type of workload. And that's kind of my conclusion. We have a demo tomorrow where you can see this operator, but also 2 other operators, and they're all integrated together into one database, and we can run multiple hardware operators concurrently. And you just have to come and look. It's really interesting. Thanks.
Any queries where the pattern vary, not just fixed pattern, but arbitrary pattern?
Repeat the question.
If we had a workload where the pattern changed, so in our evaluation, the pattern was was fixed for a specific run, but we reconfigure these regular expansions for each query every time. So we every time generate this configuration vector, and every time it's sent to the FPGA, it configures itself, and then we run the query. So we could easily swap out this configuration vector.
If you had a per row of that vector, what would the overhead be?
I didn't understand your question.
row regular
Simple
expression.
standard, for instance, the pattern could be a function of any column, and it could be different for every row.
It will be different for everyone. Oh, so that means essentially the input is another row. The expression is stored in another row. Yeah, then we have to kind of change our layout a little bit, because you would need to read this. Essentially, we would read that row first, generate all these configurations, and then load them somehow at the same time as we read the data. That's a little more involved. Yeah.
So I wanted to ask about size limitations in terms of regular expression size. So you did mention that you use compression, but how soon do you need to, I mean, at what size do you need to start to compress? And also with compression, how large or can given how large do you get before your system kind of fills the FPGA and can't increase further, can't scale further?
Yeah. So first, we always try to compress, because actually increasing the character encoder is easier than increasing the NFA. And secondly, we did some experiments in the paper where, so currently the NFAs run at 400 megahertz, and then we try to explore the space, how many characters we can support until we have to essentially go to the next lower clock, which on this platform is 200 megahertz. So you do have this trade-off. If you see like you need much more states or characters, at some point you can reduce the frequency and thereby half the throughput, but you then get more freedom for more complexity. So there is this trade-off which we explored in the paper, and we have a graph for this. Yeah. But yeah, this is a trade-off in hardware.
Yeah. Okay, let's thank our speaker again. For those who are following us online, we are going to stop the live streaming for 20 or 25 minutes for this talk. Okay, so our second speaker is titled Ken Kara. Ken, back to live streaming.
Right. Hello, everyone. Hello, everyone. Can you hear me? All right. All right. So, thanks for attending my talk. I'm Kaan Kara, and this work was done together with Jana Gitava, who's sitting right there, and also Gustavo Alonso, our supervisor. So I'm going to talk about FPGA-based data partitioning today. So we all know that partitioning data is necessary and expensive. It is a well-studied problem for general purpose processing. For example, I will mention some of the related work here. So Manigault and others have shown in 2002 already that partitioning that produces cache-fitting hash tables leads to the fastest hash join. However, we all know that data sizes keep increasing and cache sizes do not. So higher fan-out and fast partitioning will keep playing an important role on application performance in the future. So for partitioning, also many CPU optimizations have been explored. Some of the most important ones include software write combining within cache size buffers used by Balkesen and others. Then Wassenberg and others proposed using non-temporal writes using vectorized instructions to bypass the cache and write directly into the memory to avoid cache pollution. And of course, we can do multi-core parallelism. We can utilize the whole CPU to do partitioning. So in short, what I mean to say by this is we know how to do partitioning using a modern CPU. And that's why in this work, we are trying to answer this question. Can we perform data partitioning more efficiently using an FPGA? And why an FPGA? Because FPGAs are becoming very widespread. So the recent release of F1 instances by Amazon, and then the Catapult project from Microsoft, and the acquisition of Altera by Intel, all point to a future data center where FPGA is a cornerstone processor. And we need to understand how to use that processor to perform certain types of workloads. But before moving on, let me first try to explain you why would an FPGA be good at partitioning data. All right, so partitioning can be represented as a data flow where three things happen. First, hashing happens to determine where a tuple belongs to, which partition a tuple belongs to. Then the second step, we want to do some write combining. We want to combine the tuples that belong to the same partition to avoid the amount of, to reduce the amount of random accesses we do. Then we do write back where we determine the end address for the combined tuples and we write the tuples back to the memory. Now, if you imagine partitioning as a data flow like this, we have a couple of advantages on the FPGA. The first thing that we can do is we can actually implement arbitrarily complex hash functions on the FPGA without suffering any performance. So the the effects of choosing the right hash function for database operators have been studied by Richter and others in VLDB 15, and we in our own work have shown that we can implement very complex hash functions like simple tabulation without suffering any performance in FPL 16. All right, the second thing is we can also do write combining very efficiently using the large internal buffer space of the FPGA, which we call block RAMs or BRAMs for short. And these block RAMs provide a very high bandwidth distributed memory on the FPGA logic. Apart from that, we can also use the custom logic capabilities of the FPGA, and we can combine all these three stages, we can pipeline all these three stages of the data flow. So imagine when the first tuple is in the write combining stage, the second tuple can already be in the hashing stage, and this can be, these operations can happen in parallel. And last but not least, we can also do scale-out parallelism. So we can instantiate this data flow multiple times if we have enough resources on the FPGA.
It is worth mentioning here that the FPGAs at each iteration, each family of FPGAs are becoming larger. So in the future, it will be even easier to use this scale-out parallelism more. All right. So let me introduce you the target platform that we use to test these ideas. And it's actually the platform that David has already presented. It's the Xeon Plus FPGA. I have just a little bit different representation here, but it's the same thing. So we have a two-socket machine. On the one socket, we have an FPGA, and on the other socket, we have an FPGA. On the one socket, we have a CPU, and on the other, we have an FPGA. And the FPGA can access the main memory using the cache-coherent QPI interface. So any accelerator that we implement on the FPGA can work directly on the main copy of the data. And this architecture is important for us because we would like to perform partitioning on the FPGA, and the resulting partitions should be used later on by a CPU. We would like to perform hybrid operations, and that's why having a shared memory architecture is very important, as I will show you later. However, there are some limitations in this platform, as this is an experimental platform, such as the memory bandwidth, which is around 6.5 gigabytes per second, and also the cache coherence protocol had caused some problems. I will explain more in the evaluation, and I will explain why this is a limitation currently. All right, so specifically what we want to do is we would like to perform a hybrid hash join, hybrid partitioned hash join. So the partitioning should happen on the FPGA, and the build and probe stage of the join should happen on the CPU. And in the end, we would like to evaluate the performance of this and to see if this type of hybrid execution is really efficient or not. So to clarify how the hybrid execution works, let me walk you through a high-level diagram here. We have, again, the FPGA and the CPU, and we have the main memory, where we have the tables R and S. So first, we pass the pointers to the FPGA. Then the FPGA reads the tables and produces the partitioned RNS along with the histograms that contains the counts for each partition. And then the multi-core CPU can do build and probe in a shared nothing fashion using the 10 cores, and each core reading its corresponding partitions using the histograms. So this is how the hybrid join should work. All right, now let me show you the FPGA-based partitioning implementation in detail. And I will walk you through the pipeline, this pipeline, so that the efficiency of this becomes very clear. As you can see here, the partitioning works on cache lines, that is the data width of the QPI, and it is able to accept and produce a cache line at every clock cycle, so no internal locks are necessary. So first, let me describe each module here so that this diagram becomes familiar to you. First, we have the hash function module that does hashing and determines which partition a tuple belongs to. And we have, as you can see, we have 8 of them, since we are processing 8 tuples in parallel. Second, we have the write combiner modules that the tuples go into after a FIFO. And on the right-hand side here, I'm showing you the internal design of one write combiner. And lastly, we have the write-back module that reads the tuples in a round-robin fashion from the write combiners and writes them back to the main memory. All right, now that we are somewhat familiar, let me actually walk you through how this pipeline works for partitioning data. So when a cache line is received, the tuples first go through the hash function to determine their partitions. And in this example, we are assuming that the hash function is the alphabetical position of a letter. So all the tuples are hashed in parallel, as you can see. In the next cycle, we begin to see the advantage of having a specialized D pipeline on the FPGA. So as you can see here, a new cache line has arrived. And while these tuples go through the hashing, the older tuples that have arrived in the previous cycle will go through the write combining process. So let's see this happening. So as you can see, everything happened in parallel and in the same clock cycle. And this is the advantage of having a pipeline on the FPGA. Now let's focus on the insides of the first write combiner, where a tuple is received. So 3 is the hash and C is the value. So here the current fill rate determines which block RAM the tuple will be written to, and its partition determines the address inside that block RAM. In this case, let's assume all the buffers were empty, and thus the tuple will be written to the first block RAM. And as you can see, the fill rate has been also updated. So we repeat this process. We write the tuples to their corresponding partitions until a full cache line is assembled. And when that happens, we notify the next stage of the pipeline so that these tuples are read from their block RAMs and put into the FIFO. And at the same time, we also reset the fill rate that is inside that block RAM. Then the next stage is the write-back circuit reads that cache line from the write combiners. And here on the write-back module, we have two block RAMs to determine the end address. The first one holds the prefix sum for the histogram that can be optionally built in an initial run over the data. I will explain more on that later while discussing the operation modes. And the second block RAM holds the counts of how many cache lines have already been written to the memory to determine the end address. And that's it actually for the core design. So if something is not clear here, I'd be happy to discuss offline and answer your questions in detail. All right, now let me talk about different modes of operation that we have implemented for this design to increase its flexibility and its usefulness for as many applications as possible. The first parameter decides how the output is formatted. First one we have is the so-called hist mode or histogram mode. And in this mode, we actually do an initial pass over the data to build a histogram inside the FPGA. And thus, we save the size of each partition and use that during the second pass to write back the tuples. And the advantage of this approach is that the memory consumption is minimum and it's robust against skew data. The disadvantage is that we perform two passes over the data. Then the second mode is the padding mode, where we assign a fixed size to each partition and we calculate this size according to a formula, number of tuples divided by the fan out plus some padding. And the advantage is that we only have to do one pass over the data. However, if a partition gets filled during the process, we have to abort this and we need to start over. The second parameter decides if we have a row store or a column store. So first, in the first mode, the record ID mode, we assume that the tuples are an X byte key and an Y byte payload. And in this mode, we can read these tuples directly and partition them natively without doing any changes. And in the second mode, the virtual record ID mode, we have an X byte key and the Y byte payload stored separately in memory. So if you want to partition on the keys, for example, we only read the key column, but then we have to append a virtual ID on the FPGA to enable later on materialization. If you don't do that, the reshuffling during the partitioning process would make the materialization impossible. The advantage of having virtual ID mode is we need to read less data in total, and this is good because our implementation is bandwidth bound right now. And disadvantage is the materialization cost, which is however not so different than any column store that has to perform materialization. All right, now let me show you the partitioning throughput that we achieve with our implementation compared to related work. All these results are for a fan out of 8,000 and a tuple size of 8 bytes. The first bar is from Polychrono and others in SIGMOD 2014, and the throughput is achieved with a 4-socket machine and 32 cores with all the known optimizations enabled, such as software write combining. The second bar shows the FPGA-based partitioning throughput from Wang and others implemented using OpenCL. Now, the blue bars show the throughput of our FPGA-based implementation. And as we can see, depending on the mode of operation, the throughput changes. So the slowest one is the histogram row ID mode, because the two passes over the data have to be performed, and the key column is read. And the fastest one is the padding virtual row ID mode. So the light blue bar shows the partitioning throughput using the 10-core Xeon CPU on the target platform, and we see that the throughput is very similar to the fastest one that the FPGA achieves. However, keep in mind that this is because that the current implementation is bound on the memory bandwidth available in the current platform, which is 6.5 gigabytes per second.
QPI, right?
QPI bandwidth, exactly. So on the right-hand side, I'm showing you the internal processing rate of the circuit for the partitioner. And how we measured this is actually we have implemented a wrapper inside the FPGA that emulates QPI behavior, however with a bandwidth of 25 gigabytes per second. And as we can see, the internal processing throughput is much better, and if we have a platform with 25 gigabytes per second, we will achieve this throughput. We have also made possible to increase the tuple size that the FPGA-based partitioning can handle. It can handle 16, 32, and 64-byte tuples with minimal changes to the architecture. Notice here that as we increase the tuple size, the write combining actually becomes less challenging, and it decreases the complexity of the circuit, which is good because we use less resources on the FPGA. The processing rate remains the same for all these variants. All right, now let me move on to the evaluation. However, before I begin showing you the numbers, I will introduce you the workloads that we have used. We have 4 different key distributions we use for our workloads. The first one is a linear distribution where the keys are unique from 1 to n. These represent just IDs. Then we have randomly distributed keys. And we have some special distribution called reverse and reverse grid, which represents strings and address patterns. And these will show where the hash partitioning becomes better than the radix partitioning. Then we have 5 different workloads. Workloads A and B use both linearly distributed keys, but the build and probe table sizes vary. Then workloads C, D, and E have all equally sized tables, but the key distributions are different, selected from the above table. And these workloads, like I said, will hopefully show you the robustness of hash function used. And the time that we spend on the build and probe will change whether we use a hash partitioning or a radix partitioning. All right. So now let's take a look at the hybrid join performance. So we fixed the partitioning fan out to 8000, which gives the best performance for build and probe. On the x-axis, we have the number of threads that we use to do CPU partitioning and CPU build and probe. And as we can see, the FPGA partitioning in padding row ID mode is faster until 8 threads on the CPU are dedicated to doing partitioning. So we observe that the hybrid processing seems to be performing well. The only artifact that we are observing here is that the build and probe after FPGA partitioning is slightly slower. So we investigated why this happens, and the only reasonable explanation that we came up with is the presence of a cache coherency protocol that is designed for a homogeneous multi-core system. And the same protocol is used here for a heterogeneous multi-socket system, where the FPGA has only 128 kilobytes of last level cache. And since this is the case, and there is no snooping filter on the CPU side, this causes some problems. And more details about this is explained in the paper if you're interested. However, this problem should not occur in the second version of this platform. We performed the same experiment with workload B, where the table sizes are different by an order of magnitude, and the results seem to be very similar to the first experiment. Now I would like to see if hash partitioning versus radix partitioning affects build and probe performance. Here we have workload C, equally sized tables, and randomly distributed keys. On the x-axis we have again the number of threads we use on the CPU. And as we can see, hash partitioning takes longer than radix partitioning on the CPU. On the FPGA, we use only hash partitioning because there is no difference between the two. However, when we look at the build and probe, hash partitioning is not significantly beneficial for this workload. It makes sense because the keys are already randomly distributed here, and even radix partitioning creates uniform partitions. Now let's take a look at workloads D and E, which have again equally sized tables, and now we have this grid and reverse grid distributions. For these distributions, we know that radix partitioning does not achieve uniform partitions. And this shows itself in the build and probe performance. For workload D, it's 11% slower, and for workload E, it's 35% slower. Thus, we can see the benefit of using a robust hash function, which the FPGA can do without any performance reduction. All right, let me conclude here. So we have presented a fully pipelined, flexible FPGA-based partitioning that is designed to work on hybrid CPU FPGA platforms. We integrated the FPGA partitioning into a hybrid join where partitioning happens on the FPGA and the build and probe happens on the CPU. And since partitioning is a very important sub-operator, the proposed design should be interesting also for other types of hybrid workloads, not just for joins. We showed that hybrid execution is comparable to a 10-threaded CPU execution despite the limitations of an experimental platform. And this work in that regard should be received as a proof of concept for the potential of future of heterogeneous architectures. So we believe to have shown that FPGA is very efficient at doing robust high fan-out data partitioning. And therefore, in our future work, we plan to use this in a multiple of applications. So the first one is that we want to do is we want to implement this partitioning over the network for doing distributed large-scale joins. Then we want to integrate what we have here into an in-memory database, more specifically MongoDB, and have this FPGA partitioning as part of the MongoDB join to accelerate analytical workloads. And we also want to investigate partitioning compressed tuples directly. So imagine if you want to partition a table where the tuples are 5-bit or 3-bit, like these weird bit cases, and you want to partition the table directly, we can do this on the FPGA. However, on the CPU, you have to first decompress and then partition. So this is, again, an interesting case for this work. And that's it. Thank you.
One question?
Shimin Chen from Chinese Academy of Sciences. So how do you deal with virtual to physical address translation in FPGA?
So the FPGA works directly on physical addresses in that case. And how we deal with this is we have a page table on the FPGA side. And the software library allocates a chunk of memory. It can be as large as 16 gigabytes. And then the pages are 4 megabytes large. And each address for that, for each page, the address is written to the FPGA, to the page table, so that the FPGA can directly work on physical addresses.
So I'll take just one more question here.
Sure. Okay. Probably you could hear me without it, but like, so I mean, the main problem here is like the memory bandwidth, right? So you're memory bound. That's
Exactly.
what I saw in your results.
Right.
So my question is like, how can the FPGA help you, go beyond that, right? Like, can you use memory, do something, use work in the CPU while the FPGA is partitioning? If the CPU is also memory bound, then what will you do? Like you're still stuck in the CPU, right?
You mean that if the CPU is memory bound?
Yeah, I mean, like if the CPU is memory bound, then you can't do any useful work either case, right? Either you will use your CPU and saturate the bandwidth, or you will use the FPGA and saturate the bandwidth.
Right.
Right. So how can you use the FPGA more creatively there to do something more?
Right.
That's what I'm saying.
Right. So for the CPU, in order to be bandwidth bound, you need to allocate at least 8 cores. So you have to use most of the CPU resources. That's one thing. The second thing is the FPGA is bandwidth bound in this one, but as I said, the bandwidth of FPGA platforms are also increasing. So we should see large benefit in future platforms where the FPGA bandwidth is larger. And then third of all, we can also imagine this as a hardened macro. So this is as this is a specialized circuit, it can be part of a CPU architecture to do like a specific partitioning operation, and that's why also it's interesting.
Okay, so let's thank the speaker again. So our last but not least talk. So coming back to GPU, so we start with FPGA talk, then GPU, then FPGA. We end with GPU here. Okay, so this talk from Ken Po. So I think he's going to read the title because the title is too long for me to read.
So the title is Template SkyCube Algorithms for, yeah, I actually can't remember, it is too long. But it's a dense paper, so it has a lot of keywords. So, hi, I'm Kenneth, and I'm from Aarhus University, and the title is Template SkyCube Algorithms for Heterogeneous Parallelism on Multi-Core and GPU Architectures, where the "and" is actually the most important word. I'm from Aarhus University in Denmark, and this is joint work with Sean Chester from NTNU, Darius Glauskas from EPFL, and my supervisor, Ira Ascent, also from Aarhus University. So, in this talk, this does not work. Okay, I'll go over here. So in this talk, I wanted to just give you a quick outline of what I'm about to say. So I want to talk a bit about the challenges of heterogeneous hardware, especially using all multiple parts of a heterogeneous system, and introduce what we believe is their algorithmic solution for doing so at an abstract level, which is called templating. Then I want to show you a bit what a skyline and a SkyCube is, because this is our application for this idea of templating for hardware, and show you how can we apply templating for hardware to SkyCubes, some select results, and finally a conclusion. So first, why are we even considering heterogeneous hardware? So physical limits means we are hitting a bound of how many transistors we can put into a single chip. So we are going to have multiple chips in the system on one hand, but we also need to start thinking about how do we use those transistors. CPUs are very general purpose. They can handle a very wide workload, but that also means it has to handle a wide workload. Accelerators such as FPGAs, GPUs, many integrated core systems, all have the luxury of using those transistors differently to be better at specific workloads. So GPUs trade off core independence to have more cores but step locking threads. FPGAs, as we've seen multiple times today, trade off the general ALUs for having very efficient hardware programmed units, and many integrated core systems trade off the general purpose ALUs for very wide vectorized SIMD lanes. So can we consolidate these differences in a way so we can use all parts of a heterogeneous system to solve a single task in a meaningful way? And if so, how do we do that? And we believe the answer is yes, and using templating for hardware. And this draws inspiration from the world of object-oriented programming, where you have the template design pattern. So this is an example of a template algorithm as we've been envisioning it. And the idea is on the left here, you have a hardware agnostic template for doing something. In this case, a modified merge sort. So the first task here is to load and partition the data linearly. And this can be done quite cheaply on a single thread, so we don't add any parallel resources here. Then in the next part here, we're gonna try and sort each of these partitions. Now this is an expensive operation, right? So this we want to expose as what we call a hook. And the idea is that we expose each partition as a task to be performed. We then have implementations on the right here that are hardware specific to do this task. And of course we can sort on all of these platforms, right? But we invert the control as we do in templating. So rather than having a scheduler assigning partitions to each of the devices, we implement our hardware specific implementation so they ingest tasks to be executed from the main template. So we will have basically a thread running for each hardware to ingest tasks as they are ready to process them. And this gives us and to do so, we need to expose the task, in this case partitions, some expected level of parallelism. So are we going to use a single thread on the CPU, or going to use all threads to do a single task? And what's the input and output, okay? And this gives us the advantage of separation. So we can have a very complicated template algorithm that, in terms of flow, which is hardware agnostic, and then only take those tiny loops and make implementations with the inversion of control to actually perform those tasks. And so here in the second part, we would merge, once we're done sorting partitions, we would be merging the partitions. This is something that's hard to do on the GPU because merging two partitions is somewhat inherently sequential, so therefore we don't have a GPU implementation for this step. So not all hardware platforms would fit all hooks, but the idea is that if most do, then we can get good performance, as I'll show you later. But first, this was a very simple sorting example, right? Can we do it on more advanced scenarios? And for this, I'm going to introduce you to the SkyCube. So a SkyCube is a collection of skylines. So what is a skyline? And I'm going to introduce that to you by a small example. So consider buying a new laptop as a student. I think we've all been there. There's a good chance we want a good battery life because power outlets can tend to be scarce, right? And if you consider the right here, that's a collection of laptops, and we sorted them so we have a high battery life towards the bottom. But we probably also want a cheap computer because, well, at least I wasn't a rich student. So you want so the origin here is like the best trade-off, and the skyline computes all the best trade-offs in this data set. But these two dimensions or attributes are maybe not what everybody cares about, right? Every person has his or her set of preferences that they want to optimize on. So what the SkyCube does is that it consists of all possible it computes the skyline for all possible combinations of attributes. So we get to the type of data cube. And so for D attributes, we need to compute 2 to the D minus 1 skylines. This is a very expensive problem. We might want to use an entire heterogeneous machine. So this is a good first application of this idea of templating. And so for 3 attributes, we get these 7 different sets of attributes for which we can compute a skyline. So this is just the combinations of 3, combinations of 2, combinations of 1, okay? So how would we go about doing that? Well, before we get there, I want to give you a bit of terminology just so we're all on the same page. And the first is that as SkyCubes are derived from the concept of data cubes, a skyline in a SkyCube is also called a cuboid. And there is a inherent property of the problem of skylines that we can actually compute a superset of the skyline called the extender skyline, which has the property that it will contain all skylines for subsets of attributes. So if we compute the extender skyline for the first entry here, that can be used as a reduced input for a child cuboid because that's a subset of attributes, okay? And so we're going to be using this extensively. So this is the problem at hand. Compute all of these cuboids using all available heterogeneous hardware. And in our initial run of this, we've just used CPUs and GPUs, but we do believe that it is generalizable to other platforms as well. So our first template for this is called single thread, single cuboid, and it draws heavily on the state-of-the-art algorithm for this, which is actually sequential. So what that does is it computes each cuboid in a top-down manner, computing also the extender skylines and using parents as input, but fully sequentially. And so what our template does here is that first, well, it loads the data. That's just as any task. Then we expose a hook that is compute the skyline and the extended skyline from the full data set. So computing this guy. And that's just a single task, but we instruct whatever algorithm that hooks in to use all available threads. So we can do this either using a full CPU or full GPU, whatever runs the fastest. Then we have another hook that is because now we want to compute the remaining cuboids. And so the next hook is, well, for each of these levels in the lattice, using a single thread, compute the results for a cuboid. And the reason we use a single thread here is then we can run multiple sequential algorithms concurrently. If we instructed each hook to use all cores, trying to use all cores twice leads to poor performance, right? Well, it can at least. And so this is our first template, and we notice we don't have a hook down here, and that's because we don't have a sequential skyline algorithm for the GPU. And of course we will be computing for the next level as well, and this is our first template. And now the next template I'm going to introduce to you is very similar, so see if you can spot the difference. There's a change in the title here, which goes from single thread to single device, and down here we go from one thread to all threads. So that's basically it, but it makes a huge difference in the actual space of exploration in terms of using hardware, because now we can use parallel algorithms. So we can actually hook in parallel algorithms. So the first hook here is the same, and we would need to use either, in this case, a CPU or DPU, but there's also an FPGA Skyline algorithm, so we could also use an FPGA for that. I don't include that here because we don't have it in our experiments in a lack of hardware. But the idea is then in the second hook that we expose one Skyline to one device at a time. So imagine the case where we have, and of course, any compute can be computed either on a CPU or on a GPU. So whatever device is available to do the computation will let that hook implementation ingest the task. And so first, let's have an example. Oh, this covers stuff here. Let's just hide that one. Oh, I can't. Shit. That's not. Oh, huh? So did I just stop the streaming? Okay, good. So we have an example with 3 devices, 2 GPUs and 1 CPU. And so we can now assign 1 cuboid to each device. So we do parallel computation for each cuboid and parallel across multiple devices at the same time. So we have 2 levels of parallelism, you can say. And of course, we can do that again at the next level. And we compute 1 level at a time. So we have this reduced input from our parent. Okay? So these 2 templates are to a certain extent adaptations of existing work. So this idea of the extended skyline is previous work. This idea of iterating this lattice is also previous work. We're the first to do it in parallel, but like when you do one independent operation at a time in the lattice, it's not hard to do it in parallel, right? Well, it is, as I'll show you later, but intuitively it's not. So what if we start out from scratch and just say we take the template, now we want to design a SkyCube algorithm that matches our template. And this is what we call the MDMC template. So multiple devices, multiple cuboids. And their first hook looks kind of similar to what we had before. We still compute the extended skyline. But this time we actually build a search tree on top of that extended skyline. And this search tree have the very distinct property that we can iterate it on, that is built to be iterable on multiple hardware platforms. So we can actually iterate it efficiently both on the CPU and the GPU. And I believe also at least many integrated core systems in terms of what I've been doing of prototyping. So why do we want to build a search tree? Well, we're no longer going to compute each cuboid at a time. We're going to take each data point from this extended skyline and figure out which of these cuboids does that belong to the skyline for. So that means we're now exposing a parallel task for each data point instead of each cuboid. And we typically have many more data points in the extended skyline than we have cuboids. So we have more tasks, and each task is cheaper, so that we have a finer granularity in terms of the parallelism. And this will this is very important for workload distribution, because as we don't have a scheduler, but we let the hooks over here ingest the tasks. If we have more cheaper tasks, then the automatic distribution of workload works better. I guess this should be kind of intuitive, yes? Right. So that, and of course another important thing here is that we have no ordering of our second hook, right? So all tasks are exposed at the same time and we don't have any synchronization. And by having this search structure we can use on multiple devices, each of these tasks are actually quite cheap to execute. And any given hook can ingest as many tasks as it wants at whatever time it wants. So we don't stop execution at the end of a lattice layer, say. But we are no longer computing on a per cuboid basis. So what are we actually computing? Well, for a given data point, P, for example, we might find that it is in the skyline of the green nodes, but not in the skyline of the red nodes. So this is basically the output we get for each data point. And that means it actually becomes sort of a reverse index beyond computing the SkyCube, because now you can say, for this computer, my feelings tells me I like, what is it good at and what is it bad at? Or if I'm a hardware producer, in the SkyCube, what is my computer good at? It could be good at all three, mostly maybe because of the battery, or it could just be very cheap, but rubbish at both battery and weight. So this gives us another dimension to the SkyCube by switching the dimension on which we expose parallel tasks. Right, okay. So in theory, this looks kind of nice, but does it work? Like, that's the important part here, right? So we ran some experiments. We had a dual socket Intel server with 2 × 10 cores and 3 GPUs, 2 980s, which is the Maxwell generation, and 1 Titan, which is the Kepler generation, for those of you interested in that kind of thing. And all reported results include transfer times to and from the GPU, so we're never cutting corners anywhere here. And we have 4 algorithms we run on. So STSC, SDSC, and MDMC, the 3 at the bottom here, are templates implemented with state-of-the-art, modified versions of state-of-the-art Skyline algorithms for the CPU and the GPU, whereas the PQ SkyCube algorithm here is a parallel version of the previous state-of-the-art SkyCube algorithm, because that's a sequential algorithm that computes based on this template, just 1 qubit at a time using parents as input. And so we can, following our STSC template, we can actually make that parallel by just saying, okay, run multiple sequential algorithms concurrently for each layer. Yeah? So first, how does that scale on a CPU? Well, mostly okay unless we are considering our competitor. And this is like, we actually have in the paper results showing that our competitor gets a speed up from our parallelization, not a slowdown for a single core. But the moment we get to more than roughly 2 cores, it flatlines, and I should say on the left here, we are running on 1 socket, and on the second, we are running on 2 sockets. So this is basically showing NUMA effects. And the reason why this PQ algorithm doesn't scale that well, I'll show you later with some actual numbers, but it is because it uses a pointer-based tree, which is thrashing their cache. The other algorithms, on the other hand, all scale fairly well with the hardware, with the MDMC algorithm actually scaling more or less perfectly, and it scales even into hyperthreads. And this is due to the fact that we've designed it towards the template. We're not just trying to adapt something, we actually designed it towards this idea. But what about throughput? So you can have a very scalable algorithm that runs slow, right? So how are we doing on running time? And this is synthetically generated data sets. On top, you have an anti-correlated distribution. At the bottom, independent uniform. On the left, we vary dataset cardinality from 100K to 1 million. And on the right, we vary attribute amount from 4 to 16. And so the first thing to notice here is that these algorithms more or less follow the scalability plots we had here. And we've tried to be as honest as we could, so we're actually running some of these with slightly different hardware configurations based on how they performed best in the scalability experiments. So we first did scalability profiling, then we chose based on that what hardware should we be running on. So this is not an exact apples to apples comparison, but it should be clear that the PQ algorithm from poor scalability are orders of magnitude slower. And the other algorithms, depending on the workload, either follow each other, although notice the scale here from 10 to the 2 to 10 to the 8. So it's a big scale to match. And generally speaking, the MDMC algorithm again performs best, followed quite closely by the STSC and SDSC algorithms. And why is that? Why is the PQ running so much slower, and why are the others running better? So we went, and this is a bit of a throwback actually to this morning's keynote, if you were there, with Anastasia, because she talked about these clocks per instruction. This is cycles per instruction, right? And these are the numbers we have for these 3 algorithms. And notice PQ actually runs on a different scale to be able to see the differences. And so this is the issue that we run into with the PQ algorithm. We get to a point where it's actually every second cycle is idling. Whereas our MD algorithm actually on average across the entire execution runs 2 instructions per cycle. And we max out at around 6, and we go down to having periods of stalling as well. So this is not like a flat line, but on average we get to quite good performance numbers here. But that's one thing, of course. That's how it looks. But why do we get there? And so if you look to the right, we have, as Anastasia showed as well, actually, the amount of cycles we are stalling because we're waiting for memory, having missed the L3. So we've gone past the L3 to memory. How many cycles are we waiting there? And as you can see, our MDMC algorithm runs at 10 to the 8 versus the PQ at 10 to the 12. So having that many more cycles stalling in algorithms that, in terms of like effective operations, are almost similar. This MD is a bit more efficient, but not by a lot. This is basically this is why the MD runs better. So an important takeaway from this is templating works, because like these three are three different ways of using templating, but you need to make sure your hooks are optimized for where you're running, right? Okay, so finally, running with GPUs as well. We add in GPUs here. Solid lines are only the GPU runs, and the dashed lines are actually 2 cores, 2 CPU sockets and 3 GPUs, all running at the same time. And the interesting thing to notice here is that we actually get a more or less constant speed up as we vary cardinality. So we actually get a linear speed up as we add GPU. So we go from 1 to 3. We cut the running time to 1/3. So this actually scales very well, despite the fact that we have this loose coupling between the template algorithm and the implementations. So to conclude very quickly, this is actually one of the most interesting plots, I think, of the entire thing. So it's a shame they put it at the last. But this is workload distribution. So we count the amount of tasks that go to each device. So the black is the CPU, and the 3 colored ones are the 3 different GPUs run on the SD and the MD. So it's not just MD that scales well. Our SD template actually scales well with GPUs too. And no piece of hardware provides less than 20% of the running time. So what this means is that all of them contribute significantly to the solution, so we can't just cut one out. So we have a good distribution across all hardware. And yes, and so this shows us that we have scalable solutions with limited NUMA effects, at least for MD, cross-device computation scales with GPUs, and on a real-world data set, as you can see in the paper, we get a 4K speed up over this sequential PQ SkyCube. Thank you.
Thank you. Any questions? I have a quick question. Yeah. So everyone is looking for the coffee break now.
Yeah,
okay. So
makes sense.
Let's thank the speaker again. Thank you, and thank you everyone for staying time.
Cool. I thought it was 25 minutes, not 20 minutes.